So hi guys, welcome to the topic of magnetic effect of current. This video covers maximum in depth of knowledge in minimum possible time. So now we move to the 23rd day of our revision strategy pattern on covering the chapters of physics. Apologies, my voice is not very good. In fact, I'm using cold water. I said cold, hot water to actually make this video because I have promised and I want to stand on all my promises. So apologies. If you are not hearing well, you can kindly use your earpiece to hear me very clearly. So I will start with the first question. We have talked about magnetism, and under magnetism, I've talked about most of these concepts. It is only the remaining part of it, which we call magnetic effect of current. I want to talk about magnetic effect of current. I'm not here to teach. I'm here to give you quick revision on how to get answers to all these. So it simply means the ability of how current behaves like a magnet. You know, we say magnets have two polarity, the north and the south poles. So they obey the law of magnet. So keep that at the back of your mind. And they have a lot of applications. We want to talk about magnetic effect of current from basic levels. There are a lot of applications, just shorty concept. Excuse me. Now, one of the applications is electric bell, which you might have studied, telephone earpiece. We also have magnetic relays, shorty concept. You can write it down. I can also talk about lifting devices. There are a lot. The way they come to my head, devices. You can talk about magnetic separators. The stuff is hanging, and so on and so forth. So magnetic, still not writing, separators, and so these are application of what? The tendency of what? Of current behaving like a magnet, having north and south pole. So they obey the fundamental principle of this. The most important one for basic level is this and this, which a lot of time you have to make a distinction between electric bell and telephone earpiece. So just keep it in mind for now. It's all very simple. In the telephone earpiece, you use a permanent magnet. Important point for YX students. Permanent magnet, and there is no permanent magnet. We use an electromagnet. Please keep it in mind. In electric bell, you what we call a contact breaker. In fact, during my own school days, in those years, we draw telephone earpiece and we talk about what we can talk more. So keep that in mind. So I said it used what? Soft temporary magnet we call electromagnet. We've talked about that under the concept of magnetism. Keep that in mind. They are simple thing. Both of them have what they call diaphragm. Please, you can always also keep that on the back of your mind. Diaphragm. I just hope I am right with the spelling. RAGM. I think I'm correct, hopefully. So that's the spelling of that. So that's that about literature application of magnetic effect of current. Now, let's start with the question and face the question as to the one. So the first one, excuse me, a current carrying conductor experiences a force when placed in a magnetic field because dash. Now, basic concept. We have talked about the concept of magnetism. And under that concept of magnetism, we'll talk about what we call static charges. There are different types of charges. Charges at rest, electrostatic. We started with that. I'll be fast. We have talked about moving charges. And we've talked about the one we are talking about now is current carrying conductor. Now, when we talk about the total electromagnetic force that is produced in static charges, note, we only talk about the force we've talked about. It is what we call in static charges, they only produce electric field, charges at rest. I have said that under the concept of electrostatic. Electric field, remember we say our electric field we talk as E is equals to force per unit positive charge. So the electromagnetic force on electric field is just small letter Q times E. So the only force that can carry charge on static charge is what? Is the one that is produced only in electric field. So only electric field can exert force on static charge. Now, when we talk about moving charge, I've said this before, they produces both electric field and magnetic field. My voice is so bad. So only both electric and magnetic field can exert force on them. That's why I told you the difference between electric field and magnetic field. For magnetic field, the force of magnetic field is given as QVB sine of angle. Force is always perpendicular to your level. Now, I will take it with respect to your level. I won't give you different cases. For full concept video for A-level students, you can watch my full concept video. They are available. Now, the total force on both moving charges is the sum total of QE and QVB sine theta. In fact, in A-level classes, we call this Lorentz force. I'm not here to come and teach concept. I just want you guys to understand the kind of forces that is exerted on different type of charges. Now, the last one, which is what we're talking about, magnetic effect of current carrying conductor. In this case, this one only produces what? Only produces magnetic field. So this is the basic concept of magnetic effect of current. Basic application is the current carrying conductor. They only produce magnetic field, and only magnetic field can exert force on them. So always keep that, because they have what we call a kind of uncharged bodies. Now, static charge, electric field. Moving charge, electric and magnetic field. Current carrying conductor, only magnetic field. So this is the way we interpret the simple concept of what magnetic effect of current. That is, current behaving like a charge, having positive and negative axis. Current behaving like a magnet, having positive and negative charges. So I hope you can still hear this voice. So manage this voice. I won't be shouting that much, and I'm going to take it calm. I'll be very, very fast. So now, current carrying conductor, which is just what I explained now, experiences force when placed in a magnetic field, because conductor is they are not magnetized. In fact, they are uncharged. Magnetic field of current interact with what? External magnetic field. Magnetic field of current interacts. Now, magnetic field of current interact. I told you current behave like magnets. So for current to behave like magnet, you expect what? Electric what? That means the charges are moving. So you expect electric field to interact with what? With the internal magnet, not magnetic field interacting with that. So keep that in mind. That's a technical one. Force is due to motor principle is wrong. I hope you are there. Sorry, let us take this one very well. Let's understand. Magnetic field of the current interact, yes. Current carrying conductor. Sorry about that. They only produce what? Magnetic field. So this is the right answer. Sorry, I would have screwed that. This is the answer. Magnetic field interacts with external magnetic field. So electric field of current, they don't produce electric field. I just tell you that. Current carrying conductor is the question. They only produce what? Magnetic field. So the magnetic field interacts with what? External magnetic field. And the correct answer to this is option B. Current carrying conductor only produce magnetic field. Always keep that at the back of your mind. And this is the way you interact or interpret that. Next question. An equipment that functions as a magnetic effect of electric current is that rheostat, thermostat, electric bell, carbon microphone. Rheostat, thermostat, you have talked about rheostat under electricity, thermostat under heating effect of current, and also under what we call heat calorimetry. Now, I've looked at a lot of application of magnetic effect of current, and luckily for you, this option is there, and this is the answer. One of the application of magnetic effect of current is telephone earpiece, electric bell, magnetic relay, lifting device, magnetic separator, to mention but few. So keep that at the back of your mind. And carbon microphone does not work on the principle of magnetic effect of current. They rather work on the principle of force on the current carrying conductor, which I've still talked about as we produce in the concept of magnetic effect of current. Now let's move to the next question. Yes, the next question. A conductor of length 2 meter, there is a length of 2 meter, shorty concept, carries a current I of 0.8 ampere. Why is this in the magnetic field of magnetic flux? Flux is written as B vector. Magnetic flux is what? A vector quantity. 0.5 Tesla. The SI unit of magnetic force is Tesla or Weber per meter squared. Now, the magnetic force acting on it is that. Now, a force is generated when the wire carrying current. I've talked about this under the concept of a magnetic what? Magnetism. When a wire carrying current is placed in the what? In a magnetic field, we have what? We have a force that is generated. In fact, I told you, according to a man called Biosavage, which you may not talk about, we have parallel wires that are placed at a distance at each other. I told you when they are facing the same polarity, they will attract. All these have been talking about in the concept of they are carrying current I. There's a magnetic field which is perpendicular. Let's say 2 vertical wires separated by a distance of r. That is the way we interpret. We say the magnetic force, the wire is having a length. The length of the wire, it can be what? An infinite wire. There are different types of wire. Students should keep that at the back of their mind. There are different types of wire. So the magnetic field generated in the wire, according to a man called Biosavage law, is given as mu naught. I've done this one. I raised to power over what? 2 pi r. I said raised to power 2 pi r. So the magnetic field for wire carrying what? Current is given as u naught I over 2 pi r. Always keep that at the back of your mind because it's so simple. When you have a distance of r separating the wire carrying current, 1. Now, if the currents are in the same polarity, I said they attract. And if it is one more, we have I1, I2. You can put it if there are more than one current. So it all depends on what we are talking about. So this is an infinite wire. And this is the formula we use according to what Biosavage. It's very simple. I've talked about it under the concept of magnetism. So now, my point is, when the wire is carrying current in what? In magnetic field, we can talk about the magnetic field. If the direction of the what? Field is inside, represent it by stop, like this, stop. My voice is very bad. I'm only managing. Now, if you place a wire carrying current, I'm trying to show everything for the sake of understanding. I think I've talked about it in magnetism. And the current of the wire, sorry, apologies, is carrying current, the wire of length L, carrying current I, placed in a magnetic field B. Now, because the direction of the current is up, in fact, in basic classes, your teacher might have told you, use right hand thumb rule. But the basic concept you can always learn is this. Fleming left hand rule. We say when current is upward, current is high. Keep it in mind, the direction of magnetic field is inward. This is magnetic field B is inward, whereby the force is always perpendicular, you can say, to it. So if current is going upward, magnetic field is inward. Inward magnetic field is represented by star. Note that. But the other way around, if the direction of current is downward, quick shorty concept, these are basic concepts, and the force is placed like that, the direction of magnetic field will be what? Outward. So if you are saying magnetic field is outward, its current is downward, we represent that one by something like this. You might have seen it. We use something like this to denote our magnetic field. These are concept videos available if you need to watch, but I think this is enough for you to pass this exam. So this is just the way we relate to magnetic field. So sometimes when you see magnetic field with star like this, it means the direction of the field is inward. And if you see it like this, it means the direction of the field is outward. So for the force that is generated on this point, it's now taken by formula directly, is given as BIL. B is what? Vector quantity. Force is square vector quantity and you have what the length also what here is also vector quantity. So from here, you can now say because force is perpendicular to the field, we introduce what sine theta, which is one of the basic concepts you might have studied in your junior classes. And if you have not, there's always a first time to everything. So my point is, for you calculating the force on a current carrying wire, we say the force is given as BIL. Always keep it at the back of it. And if the wire are moving in the same direction, we use what? We say what? They attract. In opposite direction, we say they repel. These are things you have to keep at the back of your mind. And this is what we define as force on wire carrying what? Force on a wire carrying current placed in the magnetic field. So let's solve directly. I think this is a direct question. What is the magnetic field? Is 0.5. The current is 0.8. The length, 2. Sine 90. Where is 90 coming from? Perpendicular is what? Sine 90, which is 1. And when the angle is not given, you can directly use BIL and forget about the angle. But why we write it in full in some cases, the direction of force might not be what? 90 degrees. So please keep that at the back of your mind. So just multiply all these three parameters, you have your answer. That is like 1 times 0.8, and that's still 0.8. Force is measured in Newton. The answer here is what? Choice B. Just keep that at the back of your mind, and that's all about that. The next one, the next concept. Now, we have a particular special type of wire we call what? Solenoid wire. Now, like I said, your kind of questions, they don't allow you to, of your kind of level, they don't allow us to talk too much about too much of concept. It is just directly applying some formulas which we've talked about under magnetism. Now, always keep it in mind for when we talk about solenoid wire, it is just the same Biot-Savart law. What is Biot-Savart law? It is talking about a wire carrying current located at a distance away from what? Away from that position in the magnetic field. That wire has a length of what? I, a length of L. It is carrying a current of I, and we take what we call a current element, DL. So like I've taken all this on that concept of magnetism. You can watch in the aspect of I said the magnetic field for a wire carrying current is always U naught over 4 pi IDL, because some of you are used to all this stuff, sine theta over R squared. This is what they call Biot-Savart law. This is for a wire carrying a particular what? Carrying what? Wire carrying current. We are considering the current element. This is the formula. But for now, you don't need this, to be honest. For your level, I don't think you need it. Now, you can see that I said you can also use this form. Now, this is an infinite wire. And when we integrate this, we are going to get this value. So you always keep it at the back of your mind. So for this case now, we have a particular length, a particular point, whereby the what? We are taking the magnetic field through. So like I said, if we try to make what we call a kind of tight winding, magnetic field is also generated inside a what? A solenoid coil. That is a kind of wire that is wounded across each other. Now, the magnetic field on a solenoid wire, magnetic field is always noted by B vector, is a vector quantity, is always equals to what? U naught, just from Biot-Savart. I, the current in which it is passing. The currents are moving like this. This is the direction of the current, as you can see. Now, in this type of thing, we say when current is going in, inside current is the south pole. You've learned that in magnetism. Then the terminating end is always what? The north pole, whereby current is coming out. So current is going in like this. Then we wind it around each other. Then there will be what? A certain number of turns. So here we now introduce N as number of turns. All these are for a kind of A-level students where they can ask them to calculate the magnetic field of a substance, of a solenoid. When we talk about what? Infinite solenoid. This is the word we use. So always keep that at the back of your mind. So guys, what I'm saying now about basic concept, most of your questions will not ask you to calculate magnetic field. You will only be asked about the terminating end and the receiving end. So south pole is always into, north pole is always out to for a solenoid coil. There are different types of coil. We have L, old L, M, odd coil. We have what we call a toroid. All these things are not what you need. Like I do say,
Basic level is very easy to pass. Look at this question. Which of the following statement about electromagnet shown above is correct? Now, when the current flow from A to B, this is A to B, A will be the north pole. It's not correct. A is the south pole. B, these are shorty question. Now, from my explanation from current from A to B, the end A will be the south pole. Now, what about B? So this is also incomplete. When current flow from A to B, the end B will be to what? And B will be the north pole. Well, when the alternate current is passed from A will be then, well, now the correct answer to this question is option B, because we know that what? A will be the south pole and B will be what? B will be, I think they did not finish it. A will be the south pole and B will be the north pole. So receiving end is always south pole. Terminating end of current is coming out here. Current is going in here. So south is in, north is out. Keep that at the back of your mind. Magnetic field produced at that point is U naught I multiplied by N. Derivation are available on the channel. You can always watch if you want. So, but for your level, you don't need it. This is just what you need to keep in mind, and that's all about it. So, answer to this is nothing but choice B. Keep it at the back of your mind. We move to the next question. Now, which of the following statement is not correct? Which of the following statement is not correct? Please listen. About two parallel conductor carrying wire. We've talked about this in the same direction. Same direction is attraction. Each of the conductor will experience force is very correct. Each of the conductor will move if not prevented. They will move because there is a force. Forces causes acceleration. The force of the conductor will be equal. Now, it's also correct. Forces will balance because they said they are what? Parallel wires. There are concentric line of force around them. Definitely wire carrying conductor will form what? A concentric form. We've talked about that under magnetism. The two conductors will repel each other is what? Is not possible. Same direction. I've talked about it. No need to waste time. Same direction. This is hanging again. Same direction. I think it's back. Is attraction. So always keep that in mind. So the answer to this is choice E, and that is the answer to our question because we've talked about that. So the next question. In the diagram, a straight vertical wire is placed between two opposite magnetic poles, which are separated horizontally by a distance. If a current is passed down the wire, the direction of current is down. You can see. In which direction will the wire move? I've told you. Downward current. I just talked to tell you about that. You can see. Downward current. I told you about the direction of magnetic field will be out magnetic field. I just talked about that, and the direction of force is like this. Now, but always keep it in mind when we have a kind of what? Magnet separator. We have two magnets in which polarity are not the same. North and south magnets. Now, when current flows downward, it means the current is flowing in the south direction. Listen. From your polarity stuff, you know that your light poles repel. These are not vertical wires. Or light poles what? Attract. South-south, it will repel from south. Then it will come into contact with what? With the north. So north-south magnet. Whenever you have a north-south magnet, and the direction of current is going south, always keep it at the back of your mind. South means, I've told you, please, always keep it. It's very, very simple to get answer to all these things. Now, the direction of the what? The direction in which the wire will move will be upward. Please, we say downward current. Downward current, right? It is upward, and upward current, shorty point, is downward. So talking about direction of current. So always keep that at the back of your mind, very important. So downward current is upward current is what? Is downward. So northward is upward, current will be downward. So when we say current is downward, it means into. When we say current is upward, it means what? Out to. So this is the way we interpret that. We can use what? Right-hand thumb rule to also get the direction. It's very simple. But if you don't know this right-hand thumb rule and stuff like this, please just use downward current is upward, and upward current is what? Downward. Downward current is upward. Downward current means into current. is upward field, then what? Upward current is what? Downward field. I think this is direct and basic. So in this kind, if the current is passed down, downward current, which direction will the wire move? The wire will move what? In the direction what? Downward current is up feed. So the answer is what? Upward. And this is the answer to the question. Very simple. Please don't go and fall a victim of picking wrong answers in this type of question. The next one. In the diagram, if the magnetic field points into the paper and the force on the current carrying conductor points offward, what is the direction of the current? Now, this is another one. You can also, it's more or less like what I said. Always keep it in mind. When you have magnetic field pointing downward, the field is pointing downward. Keep it in mind. Now, charge can be what? This is what we do in physics. We say the direction of the current or the velocity. Current or velocity. We point towards the left if this is carrying a positive charge. Now, if the direction of, just listen, magnetic field is pointing inward and the charge here is negative charge. You know the meaning of negative charge? Positive charge is north. Negative charge is what? South. Now, the direction of the current will point to this side. Right-hand thumb rule, I think it's just better. So if direction of field is inward, I've told you we use star to represent the direction of field. If it is inward, we use star. So now, just keep it in mind that you can have positive and negative charge, which are north and south pole. So when you talk about direction of current or velocity, you know the force on wire current is BIL sin theta, and the force on the magnetic field carrying a charge of V is QVB sin theta. So that is why I'm telling you in terms of current and what in terms of velocity, so that you can keep it at the back of your mind. You don't need to be going looking for answer when you already know the direction of the answer. This is the direction, the way we talk about when magnetic field is inside. So when magnetic field is pointing inside, current is going to what? If the positive charge, if it's a north pole, current or velocity will move towards what? The left. But if this what? If it's the south pole or negative charge, the current or velocity will move to the right, and the direction of the field is still downward. Please, negative means right. Positive means left. Shorty concept. And I told you, if the direction of the field is outward field, if the field is pointing upward, outward field, we represent those one by something like 0, 0, 0. Then you cross it like that. That is the way we represent that diagram. So, and what that one means is what? Always keep that in mind. The direction of your what? Velocity. We now, if the field is outward field, look at the field. This is the magnetic field. Sorry about this. This is the direction of your velocity. If the field is pointing outward, so you expect what? The velocity or the current to be in this direction for positive charge. And for negative charge, the same thing. If the field is pointing outward field, we use something like 0, 0, 0. Then this time around, you expect what? The direction of your velocity to be what? Or current to be downward. So please keep it at the back of your mind. It's a simple stuff, which if you don't know how to place your hand, you can always use all this short concept. So my point here is, look at this question. There is a star. When you see a star, you know the direction of the magnetic field is downward into magnetic field. Now, the direction of force was said to be what? Upward. So if the direction of force is moving what? Upward. According to the question, if magnetic field is into the paper, field is not out, so I will consider these two. And the force on the current carrying conductor is upward. When force is upward, you know what it means? The direction of the force is upward. You now say, what is the direction of the current? So if the direction of the force is pointing upward, upward means north pole. You know that. North is upward, whereby south is downward. So that means the velocity of the current will move towards this side. So from your polarity, this is left side. This is what? Right side. Another question can write it in terms of north, south, west, and east. So it will move towards the west side. If the polarity is what? If the direction of the force is upward and the direction of the field is into field, you expect current and velocity to be towards this side. If it is opposite charge, which is downward force, you expect the direction of the polarity of the current or the velocity to be towards the east or towards rightward. So for this question, the answer is left, and we are going to pick this, and that's the question answer. Please, you need to visit all these things, and you need to understand it very well so that you don't make mistake. They are simple stuff. If you know it, you are going to get 100 in it. But if you don't know it, you have to carefully analyze it. Field can be into and can be out to. If it is into, we use star. If it is out to, we use 0, 0, 0. So, and the direction of your pole, north and south pole, we also tell you the direction of the velocity and current. So please take note of that. The next question. About the next question, we have two parallel wires, X and Y, carrying current 3 amps and 5 amps respectively. If the force experienced per unit length of the wire is 5 times 10 minus 5 Newton, the force per unit length experienced by the wire Y is what? Wow. We have two wires. It's a simple question. Now, from what we have studied, we said the magnetic field for two long parallel wire, infinite wire, is given by Biot-Savart. You can also use Ampere law, but I think Biot-Savart is very, very fast. Now, it's given as B is equals to B vector is equals to U naught over 4. We have I dl. dl we call current element sine theta divided by r squared, which r is the distance of separation. Now, if there are more than one, like I said, you can say the magnetic field generated in two long vertical wire infinite is given as B magnetic field is equals to U naught over integrating wire carrying current. Now, this will now give us 2. We have, like I told you, you have to be careful when you are dealing with all this stuff. Now, you can have I1, I2, because there are two currents, I1 and I2 sine theta divided by r squared. So keep it in mind. I said 2 by 4 pi, please. Infinite wire, 4 pi. U naught over 4 pi is given as a constant as 4 times 10 to the power minus 7 Henry per meter. You don't need that. So what am I trying to say here is that the magnetic field is proportional to the first current and the second current. So if it is carrying double current, you can say I squared if they are equal. But what we are talking about, dl, which we call elemental element, current element, we only consider the L. This is the experiment. There is a wire carrying current. It was positioned at a point P away from here, which is at a distance of R from P. It's carrying current I. The wire is carrying current I. Subtend an angle of theta at this point. So we only consider a very small point, elemental point we call dl. And this dl is what we call a current element. That's the physical property name. It's called current element. Like I said, to your level, you may not need it now, but later, whether you like it or not, when you get to schools, you are still going to talk about all this stuff. So we consider just elemental current. We now say we call it IDL. That is what we call current element. So it's a current with a very, very small amount of length. So we now multiply current multiplied by DL, which is measured in ampere per meter. We call elemental current or current element. Anyhow you call it is correct. So what am I trying to say now? The force per unit length, which is called IDL now, force per unit experienced by both of them is going to be equal because we only consider a current element IDL. So IDL is proportional to what? The magnetic field. So force per unit length of the first wire is going to be the same as force per, because we are only taking an elemental strip. So force per unit length is proportional to IDL. You can see the magnetic field is proportional to what? IDL. So IDL of what? The first one and the second one will be the same thing. So force experienced by unit length, which you call elemental, the current element, is direct relationship. So no matter the value of the current, keep it in mind, the force per unit length is going to be the same. So in this kind of question, you are not solving anything. Force per unit length is still the same thing, and it is the same thing as what? 5 times 10 is minus 5 newton. That's the answer to this question. It's a technical question, but always keep it at the back of your mind. But according to Bell-Savart, the force per unit length, you know, we've talked about F equals to BIL. You can start substituting if you want. Now, here you see what? B now, you can put what? You can make this a formula, it will be equals to F over IL. You can see this gets cancelled out, and at the end of the day, you see that what? The force per unit length, you can say F over L here. You can see my point is equal. I'm just showing you, because there's nothing that cannot be proved in physics. This is BI. So now force per unit length is what? It's the same thing as what? Multiplication of what? B multiplied by what? I. And B is what? Proportional to what? IDL, which we call what? Current element. So that means the amount of what force per unit length of the first one will be the same thing as the amount of force per unit length of the second one. If you substitute the formula parameter and the constant, they will still give you the same value. So please keep it at the back of your mind that it doesn't change. We move to the next one. Time is not on my side, but I just have to explain a lot of things. The next one. A vertical rectangular coil. Should I take you on the concept of rectangular coil? If time permits, of sides 3 centimeter and 2 centimeter, has 20 turns and carries 2 amps current. Calculate the torque on coil when it is placed in a uniform horizontal field of 0.1 Tesla. Magnetic field is a 0.1 Tesla. Tesla is capital T. And also write it as Weber per meter square. Now we have the current I was given as 2 amps, 2 ampere. Which other thing? We have the number of turns N is given as 20 turns. And we have the rectangular area of rectangle, because we need area of the coil, is given as 3 centimeter by 2 centimeter. Area is length times breadth. That's 3 times 2. That is 6 centimeters square, which you can convert to what? You can convert each of them to meter over 100 over 100. Because if I say this one divided by 10,000 now, I know most of you will say, where did I come about 10,000? So that is how I come about my 10,000, 0.001234 meters square. So that is that. That's the area. Now, when we talk about the torque on what? On that is produced in the magnetic field. The torque produced in the magnetic field is given as, please, like I told you, the force on the magnetic field is given as BIL. Please note that. Now it is now rotating. And when it is rotating, you introduce the number of turns in which it is now rotating. As this rectangular coil is rotating, is covering an area at an instant of time. So the area, the force generated by the magnetic field multiplied by the number of turns and the area is called the torque. So what I'm trying to say, most of your textbook will write it as BANI, B-A-N-I. Please always keep that at B-A-N-I. Please note that. Because this time around, we are cancelling out the length because this thing is producing area. Let me quickly show you. Time is not on my side, but let me let you know. If you have a rectangular coil, let's place it, depend on the orientation that is placed in a magnetic field. I told you a closed coil. We always say this, a closed loop. Whenever you have a closed loop, the force generated in a closed loop is always given to be what? 0. And how? I will show you. We talk about into field. When I use into, I'm going to use star for you to see. Let me follow simple orientation. Now, from this point, my dear student, let's say current is being carried in this clockwise direction. As you can see, the rectangular coil, there's a magnet, north and south, just for you to see. As this thing starts rotating, force will be generated. Here to the upward force. We've talked about that. Force is BIL. I hope you can see. Here it will be downward force. It will be BIL. Here it will be what? Towards the right. I've talked about that. It will be what? BIL. I can call this one BIH as the height of the rectangular coil. And here is what is also outside. This is BIH as it is rotating. So what happened? This and this gets cancelled out. This and this gets cancelled out. We say the force generated in a rectangular coil, which is a closed loop, is always equals to 0. Now, but if you have a kind of different orientation like this, as you can see, diagram not going to stay. I'm only trying to show quick concept. Now, in this case, now you have, you can see, in this case now, the direction of the area of the P is kind of different. Look at where the area, this is the area now. Magnetic field is at 90 degrees to this. So the currents are also moving. It is only these two currents that will balance out each other. For example, the area of the field is moving perpendicular to the what? Magnetic field. So we also have the same magnetic field, star, into field. But look at this orientation now. It's kind of different from that. Then there will be a what? A kind of torque, rotational force. That is what? Moving with respect to this area. So we now define the what? The torque. That is what? Moving in this type of orientation. We have north and south magnet every time. Torque is a vector quantity. It's now given as Bani, B-A-N-I, sine theta. Because the direction of the field, the force is perpendicular, and it is moving clockwise. Rotation is always inside field. Anti-clockwise rotation is what? Outside field. And area is perpendicular. So the torque generated on the field is given as Bani. So Bani is good to keep in mind. I always write it as Bina. My own textbook, you will see torque. I wrote it as Bina, B-I-N-A. So sine theta. But I think it's easy to know Bani for what? Formula for where B is what? The magnetic field, area, numbers of turns, current, and the angle of what? Of the rotation of the rectangular coil. So this is the formula we use to what? To what? Calculate the torque on what? On the magnetic field. So now, for this question now, we are looking for the torque. It is not giving us any angle. We can just write T is equals to Bani. And if you go by that, I'm waiting for this to come up. We can substitute the parameter. Our B is 0.21. Our A is 2. Now our area is length times breadth is 0.006. Just multiply, guys. The numbers of turns are 20 turns. The current is also 2. You multiply all these parameters, my dear students. If you multiply all these things, you are going to get one of the answers that is placed there. I don't have calculator as usual, and I cannot be stressing my brain for you guys now. You can quickly do that. And if you do that well, let me see. This should be like 2.4 times 10 raised to power minus 3. Torque is measured in Newton meter. So that is the answer, and that is option B. So this is the question answer. Keep that back of your mind. It's so simple when you know the concept. The next one. On which of the following does the operation of a moving coil ammeter depend? Moving coil galvanometer, moving coil ammeter. Both works on the principle of force on a current carrying conductor. So keep that at the back of your mind. Moving coil, all this moving coil, either moving coil ammeter or moving coil galvanometer. They work on the concept of force on a current carrying conductor. So always keep that in mind. Whereby telephone earpiece and all those your stuff work on magnetic effect of current. Now, the force on a current carrying conductor is given as we've talked about that. It's given as BIL, and if it's carrying charge, it's given as QVB. Always keep that at the back of your mind. This is very important. So this is a simple question. Moving coil galvanometer can be converted to ammeter. You can also calculate the sensitivity of galvanometer, which is also part of this slide, which I think the academic team is going to add to their question. So it's a simple question. It does not work on electromagnetic induction. That's our next topic tomorrow. Moving coil ammeter work on what? Force on a current conductor. So keep it at the back of your mind. Other application of force is what? Your dynamo. Dynamo, generator. You know that very well. You know, when we talk about alternating current, the direct current, all these are synchronous current and direct current to what? Alternating current. This time around, let's limit ourselves to what we have. It's a very simple question. This is the answer to that because I only need to focus on what you need and not what you don't need. So keep that in mind. Let's move to the next slide to tackle the next type of question. Now, the next question says, which of the following statement is incorrect? The sensitivity of a galvanometer. The sensitivity of a galvanometer, which incorporates an optical lever arrangement, may be increased by providing dash. Now, we need to be careful about this type of question. To understand this, let me quickly take you through the quick concept. About the quick concept, when we say current sensitivity, let me just draw a simple galvanometer just for illustration's sake, because I know most of us, we are not used to this topic in our junior classes, even in your tutorial, maybe most of the time. Because of time frame, the teacher might not be able to talk about it. Now, this is the pointer, the magnetic pointer, which is connected to two magnets. One is the north, and the other is the south. I'm just trying to show you diagram not drawn to scale. Let me extend my needle. So at this point, this particular needle here has the tendency to what? To deflect. You understand? It can go back and forth. Now, then it is moving at an angle of, I have to use arrow so that it has to be, it is always moving in such a way that it is what? Forming an angle of theta. The needle is deflecting as it is rotating. It is forming an angle. Oh my word. I'm picking up red. Okay, now that's the needle. This is the angle of theta. But we say the needle is always having what? A kind of 90-degree angle when it deflects. That is when it moves away. So now, how does it work? Now, there is what we call, at this point that it is rotating, it's always generating what we call a kind of restoring torque. We talk about torque, restoring torque. That is, when it moves back, it can move, it can deflect forward, and it can also what? Deflect what? Backward. So there is always a restoring torque. If it moves forward, it always comes back to its initial position. So there are some conditions. That means there is a torque that is developed inside this particular thing. So we've just talked about torque on acting on a force. I told you torque is given as Bani, B-A-N-I, sine theta, right? I hope you understand that. And we have also talked about this under the concept of our magnetism. We say the magnetic moment, M, is given as, please, all these things are very, very simple. Magnetic moment is the current multiplied by the numbers multiplied by A. So you can also write the torque in a current inside the galvanometer. These are quick concepts as the magnetic moment multiplied by magnetic field multiplied by sine theta. Now, there are a lot of things you need to understand. When we say sensitivity of a galvanometer, it means sensitivity, shorty concept, sensitivity of galvanometer means the tendency to measure what? Accuracy, and what? We talk about ability to measure small current. So it's very sensitive. So its accuracy is about more like 100%. So sensitivity means ability to detect small current. That's meaning of sensitivity. So now, when we talk about magnetic torque that is generated, a quick one. When we talk about magnetic moment rather, this is moment of magnetism. We've talked about it under magnetism. Now, to continue this now, we can now say, okay, as this thing is rotating, listen, it is being deflected. So it is always advisable for you to use what we call a thin suspension so that it can deflect. So we use a thin suspension that has a small horizontal control. This thing must be small. So it's always a thin suspension with small. You can say I'm laughing because it's this all this thing I'm doing for you in short time are full concept classes. I'm really trying to make it very fast and direct with small horizontal. We call it horizontal. Horizontal. My spelling is very important. Please, we have to spell well. Horizontal control. So that is what the needle is, so that it can dictate a very small change in what? In current. So keep it in mind, there is a torque that is generated, and torque depends on what? Numbers of turn, area, magnetic field, and current. So all these factors can bring together, and we now say as it is rotating, it is rotating, like I told you, it starts moving, it starts rotating. So we say the total amount of torque, which we write as MB sine theta, which was what I have written here, is the same thing as equals to when this thing starts rotating at an angle of theta, we introduce its sensitivity we call C, and what? The angle in which it is what? It has moved from this particular point to any point in which it is going to. So this C is now defined as what? Current sensitivity. So we say MB sine theta is same as C theta. So here we can now say the current sensitivity, I, is now given as C over NAB theta. So we define current sensitivity I, because I've told you what MI stands for. If you don't understand, you can write it as BANI sine theta, or BANI, because the angle is 90, sine 90 is 1. So anyhow you want to write it. This thing is hanging. I just have to wait. But time is not on my side. I'm wasting too much of time. We have to be fast, guys. BANI sine 90 is equals to C theta. For you to see it, so this is BANI as sine 90 is 1. I told you the angle is always 90, is equals to C theta. So make I sort of formula. This I is now defined in terms of C. So this particular constant that is inside this bracket, C over NAMB, is now called what? Current sensitivity. So always keep that at the back of your mind. So make actual formula is now equals to C over what? NAMB. Now, so we define current sensitivity as what? You can see theta divided by NAB. So it's always like that. Whenever you are defining current sensitivity, so C over NAB, most of the time, sometimes people write it as K. So always keep it at the back. We can also define current sensitivity as in either way. In this way, now it is measured in ampere per radian. The SI unit is ampere per radian. It can also be defined in the reverse way as current sensitivity. I can define it in terms of the angle theta. Make theta sort of formula from here. It will be equals to what? NAB over C. And in this time, SI unit is what? Radian per ampere. So the sensitivity of current can be defined in two ways. It can be what? I over C. In terms of our NAB over C, it can also be C over NAB. So sensitivity of a current, sensitivity of what a galvanometer is given in terms of C over NAB, it can be equals to theta over what? Over, we have our I equals to K theta. Most of the time, you say I equals to K theta. So K equals to I over theta. In this part, you can say theta is equals to Ki. K equals to, you can see here, if I call this one the constant now. So I can say K, it is now equals to what? Theta over I. In this case, if I call this the constant, K is equals to what? I over theta. So I do tell most of your textbook, they do have a misconception in their definition. Sensitivity of a galvanometer can be in these two ways. It can be I over theta and it can be theta over I. It depends on the SI unit. So I have seen a lot of questions, even in UTME, with all due respect to that, to UTME, There are a lot of times they only define current sensitivity as the deflection over current. No, sensitivity of a current can also be defined in terms of what? Current divided by what? It's what? It's deflection on the scale. So keep that at the back of your mind in case you see what, because nowadays all those errors has been what? Has been corrected. So and that is why we are here trying to give you maximum knowledge, minimum possible time, and for you to understand how it is being done. So my point here is that now we can quickly answer this question. The sensitivity of a galvanometer, which incorporates an optical level arrangement, may be increased by dash. A large number of turns. As the number of turns is increased, the torque is increased, the sensitivity increases. Yes, correct. A thinner suspension with small horizontal, I talked about that. Very correct. A special alloy permanent magnet, which gives a high magnetic force. Let it be known that it's also correct that the type of magnet, it is connected to a magnet. You can see my magnet. We use what? Permanent magnet. Permanent magnet. And because of that, we are trying to reduce some kind of heat loss as a result of what we call eddy current. We still talk about that under electromagnetic induction. Don't worry. So this is also correct. We use a magnet. And the last one, all of the above, we have. Now, so far so good, all of the above is correct. A light source with greater intensity. It's very wrong because there's nothing like that. Out of all the formula factor I've given to you, I never talked about what intensity of light. So keep that at the back of mind. The intensity of light does not have effect on how sensitive a galvanometer can detect small current. So the answer to this is this. E is correct, and this is the answer we are going to pick for this question. I hope students understand this, and I hope you don't have any doubt. And if you have any doubt, you can always let me know. So I hope students are getting this, and I hope you're enjoying the class. We move to the next question. Apologies because I have to explain. That is why I'm taking the time. I'm being signaled to stop the class, but I have to finish. I just have to finish. Please note that. Now, the next question. A galvanometer of 20 of resistance 20 ohm is to be provided with a shunt. Now, we need to understand galvanometer, when you say shunt means low resistance. Important point. In parallel. There's another one we call multiplier. Let me just talk about it once and for all. That is called high resistance in series. I'm going to do some, and I'll leave some for you to do and put your answer in the comment box. Please keep that in mind. I just want to do that intentionally to see if you're actually following my lead. Now, when you convert galvanometer to ammeter, you use a shunt. A low series resistance, a low parallel resistance is connected across it. But when you convert galvanometer to a voltmeter, you use a multiplier where you need a high series resistance. I hope you are jotting that down because it's very, very important you jot it down. Now, in this case, you are using a shunt, then we are converting to an ammeter. The resistance is 20 ohms. So the low resistance you need is 20. Then with a shunt that is 1/10 of the original current, please, you have to do a little bit of math. So 1/10 of the current in the circuit that is passing through the resistance of the shunt is that. There are numerous methods you can use to solve this type of question, but I'll give you the direct method. And doing that, I'm going to clean this slide so that I have space. Like I said, I'll just do few questions. If you have many of these type of questions, I'll just do few, then you are going to do some also on your own. Now, let me give you one of the simplest methods you can keep at the back of your mind. Now, for that, you can also always use the simple method. The current drawn over small letter I is equals to galvanometer current plus the shunt. Another formula you can say is I1 R1 is equals to I2 R2. This is also going to work whenever you are converting galvanometer to ammeter. But I think this one is more direct and it will reduce your doubt level. That is, directly you can just apply this formula and get your answer. Let me tell you what each of the formulas stand for, because you need to. It's important to know. Now, I is the large current. Capital I is the large current to be measured. large current to be measured. Small I is small current to be measured. Small current that the galvanometer can measure small current. G means the resistance of galvanometer. And S means the shunt, the resistance of the shunt. So use this whenever you are converting galvanometer to ammeter directly, you won't have problems. So on that, we can quickly solve the question and manage the space here. I just have to be fast. Time is not on my side again. I've used too much of the time, but you guys know why I'm actually doing that. So you can use I1, R1 equals to I2, R2 as well. And why I have to do all these things is because most of you are not familiar with this type of questions. So if it is multiplier, use this formula, the volts, this V equals to I open bracket G plus M. So here, M stands for the multiplier. The only thing I will add, the resistance of the multiplier. Every other thing, this is a small resistance, small current. This is the galvanometer resistance. Then this is the multiplier resistance. So use this. These two formulas are important to solve a lot of questions, and we are going to be using them for a lot of questions here. Let's solve this question now that we have the idea about what it takes. Now, let's quickly solve without wasting time. Now, look at this. A galvanometer of resistance, you can see the resistance of the galvanometer, that means G is equals to 20 ohms. G is equals to 20 ohms. I hope students are following. I'm not going to waste your time. Now, is to what? Is to be provided with a shunt, current of the shunt, I. Now, small I, small current is 1/10. That's 1/10 of the big I, of the current of what? Of the circuit. So 1/10 small I is equals to 1/10 of the big I. That's the meaning of 1/10 of the current that is passing in the circuit. So the resistance is what we are looking for. The resistance of the shunt, that is S, is our question. So for shunt, use this. For multiplier, use that. So I over I equals to that. Let's do that. So if small letter I equals to this, you can cross multiply. You can see that. You can just read directly. You can say capital I over small I will give you what? 10. So that's just 10 is equals to G. What is this? 20 plus S over X. Somebody saying, how did I come about that? They are asking me here, how did I come about that? What is I? Capital letter I. Small letter I is 1/10 of capital letter I. So if you look at this now. If you write this now, I is 1/10. Small letter I is 1/10. So I over 1/10 capital letter I. This will cancel out. So you have 1/10. 1/10 will give you 10. Excuse me, that's how you come about that. So please, you have to learn some basic stuff too. So here, from here, you just cross multiply. And on simplification, you have 10x is equals to 20 plus x. That is 10s minus s, algebra, s is equals to 20. S is equals to 20 over 9. S equals to 2.2. 22 ohms. So I think this is direct, and the answer to that is choice B, and that's the answer to the question. So please keep that at the back of your mind. The next question. I think we've done this one. We pick E. We've done this question. Now, in order to convert a galvanometer to ammeter, I told you ammeter means low resistance in parallel, which you call what? Shunt. So that is galvanometer to ammeter. Formula is capital I over small I. The total capital I is galvanometer resistance plus the shunt divided by the shunt. This is just what you need to put at the back of your mind in a quick way. So low resistance in parallel, low resistance shunt is connected in parallel. Option A is correct. And that is the answer for that. The next question, guys. Which of the following is not part of a DC motor? Please keep it in mind. A DC motor is just an instrument. I hope you have heard about DC motor. I told you they work on the concept of what? Force on a current carrying conductor, which we've talked about. So be careful about that. So they don't have what you call a transformer. Transformer work on the principle of electromagnetic induction, EMI. So the answer to this is this, because in your DC motor, you have a field magnet. Each of them do have a particular purpose, the purpose they serve. I can quickly tell you, if you don't know, what a field magnet does. Magnet, because it is the magnet that determines the polarity and the direction of the force. You know that. Please always keep that at the back of your mind. So we use permanent magnet to have high magnetic flux. So we use a permanent magnet. Told you when I was doing current sensitivity, to generate high flux. Flux of magnetic field is written as what? The magnetic field multiplied by its area. So note that for those of you who don't know. Now, commutator, okay, armature. Armature are found in your DC motor is like what? A generator you use in your house. So DC motor, they have an armature. That is where you have what? The combination of your what? Where your coil and your coil are being what? Stored. Now, commutator. Commutator is what? What we call the split ring. So it is what allow current to flow in what? In the particular direction. You can say one direction. So keep it in mind. So these are basic things I believe you have studied. And if you have not studied, there's always a first time to everything. And that is why I'm telling you all this stuff. You need to know them. Please keep it in mind. That is not about that. The answer to that is transformer, because transformer works on the principle of electromagnetic induction. The last question is still the question on what I have talked about. The question says a moving coil galvanometer has galvanometer resistance is 300. Gives a full scale deflection of current of 1 milliamps. You have to convert as 1 times 10 to the power minus 3 amps. Conversion is important in physics. I hope students know that. Now, the stuff here says the resistance R. Same question, same concept, same formula. I don't think I have to do this. Maybe I'll leave this for you guys to do, because it is just direct question. Please keep it in mind. It is a direct question. Direct question. So let me just leave it for you guys to do, because it's still the same thing, because you are using the formula of I over I equals to G plus S over S, which is what I've done. So the resistance out of the shunt, we are looking for S. That is required to convert the galvanometer into 3 ammeter. So the small letter I is 10 raised to the power minus 3. I have converted. The capital letter I, the small letter I, is 3 amps. Substitute and put your comment in the what? Down there in the comment section. So let me do this, because I think this is voltmeter. Now look at this question. A galvanometer of resistance 50 ohms. I'm not sure this is 50. As if I think it's 5.0 ohms, I guess, because 50 is kind of high. Has internal resistance to be 50 is too high. Internal resistance should not be more than 5 to what? 5 to 6. But it can be 50 anyway. Has a full scale deflection for a current of 5 milliampere. For a current of 5 milliampere. What is the resistance required to convert it to a voltmeter? So I think we have voltmeter question, which we can do with the formula of voltmeter. Let's take it as a 50 with a full scale deflection of that. Let's bring out the parameter. The G, the galvanometer, is 50 ohms. Then 5 milliampere is 5 times 10 raised to the power minus 3 amps. So keep that at the back of your mind. So small current I is 5 times 10 is from minus 3 amps. So which is more like writing is 0.005 amps. Then here we are looking for they said what is the resistance required to convert the voltmeter V is equals to the question with a full scale diversion of 10 V. So we can say here, just keep it in mind, we are looking for the value of V is equals to 10 V. We are looking for the value of the multiplier, because if you want to convert what do you call it, your galvanometer to a voltmeter, you require a multiplier. I gave the formula for that. I said always use V is equals to small letter I into brackets G plus M. What is V? V here is 10V is equals to, you can write it in any small letter I is 0.005 open bracket. What is your G? That is 50 plus M. So cross multiply and get your answer. It's so simple to do all this thing. When I say 10 V means 10 volt. So I may not put this, so please note that. So just solve this question. Divide both sides by 10. On simplification, you are going to have, if I divide both sides by 0.05 or whatever, to cancel this, 10 divided by 0.05 should give me 10 divided by 0.05 should give me 2000. Please confirm that 2000 is equals to 50 plus M. So my M answer would be 2000 minus 50, that's 1950. And that is the answer to this question. So B is the correct answer to this. And that is that about that. I think that is the last question. Do we still have one more? Wow, one more question. Now, I'll do this. A moving coil galvanometer has a full scale deflection of 3 amps, equivalent to 30-degree deflection. The sensitivity of the galvanometer is that. I've taken the sensitivity of the galvanometer. I said it is generally C over NAB. Or it can also be NAB over C, depending on what the examiner wants. So if it is C over NAB, we say I equals to K theta. That K is sensitivity, we say I over theta. If it is NAB over C, we say theta is equals to IK or KI. So K is equals to theta over I. So both is correct for formula for sensitivity of the galvanometer. And these are the misconceptions I do talk about in your textbooks, which you need to correct now. So because most of you just cram on what somebody has to work, you don't actually know the concept, then it gives you problems. So in this case now, you can see, now the current here, the deflection is 30. If you go by this, 30 divided by the current is 3. You say the answer is what? 10. I told you the SI unit will change. In this case, it is what? It is radian per ampere. That's the sensitivity here. But if you watch the option, all these options are in degree. So because they are in degree, basically you should put degree on top. So to get 10. But if you have done your own as current divided by this 3 over 30, you have 0.1, which is also correct for current sensitivity. But in this case, the SI unit is what? Ampere per radian. Both are correct. I am the one telling you. So please note that at the back of your mind. Both are correct. But because of the nature of the question, the SI unit here are in degree. So you put the angle up, then the current down. So 30 by 3 gives you 10. And that is why we are picking this as the answer. I hope you understand. And about the last question is PQRS is the rectangular one, in which PQ with PQ perpendicular to the magnetic field as shown in the diagram here. If the current flows like this, as a clockwise current, you can see like this. I told you about the area. The torque is equals to burning sine theta. Now I've told you about the direction. How do you get the direction for a rectangular cord? Depends on the orientation. I've explained this orientation before. And what did I tell you about this orientation? So simple. When you know something, it will be so simple. Now, you can see this is south and north. So, and this is moving onwards in a clockwise direction. So, you know, like poles repel or like poles attract. So, the coil repel away from the south pole. The coil will repel, this coil now will repel away from the south pole because you know south is downward. And this thing is moving what? Downward here. So this coil will repel away from here, no option here. It will repel away from the south pole. So the face here, the face of the coil is not parallel to the north and south. So always note that what here, PQ is said to be what? Perpendicular. You know the meaning of perpendicular field to the magnetic field. So what you expect is what, because it's south pole, the direction of this one, the coil will move in the direction that it will repel away. So the direction of the distance is always going to be in this form. It will be like that. So it will repel because north pole of the magnet will become north pole by polarity. Same pole, same polarity repel, and what's different pole or attract. The basic law of magnetism. So keep that in mind. The face of the coil near the end pole of the magnet will become north pole by polarity because south is going down, or this is south. It will repel away, and when it repel away, the direction of this thing will go in this side. So keep it in mind. This is so simple. So LiPo repel or LiPo attract. Since PQ is perpendicular, look at PQ. The conductor here is PQ. You expect what? You always expect the direction of the magnetic field to be what? To be a perpendicular field. So my point is what? It will what? It will move what? In this direction, which is repelling away from the direction of what? The direction of what? The south pole. So that's just that about this. There's no option to that. If the current flow in a clockwise direction, I've explained this before. If you follow that, I told you if it is flowing like that, the type of field that will be generated is into field, which will be represented by star, 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 star. And because the field is perpendicular, it is at 90 degrees, you expect what? The area of the field also what? To move in that direction of clockwise. So, and because of that, the field here is into field. So into field, the direction of the paper will be out. We've talked about that. It will be out. And because of that, we expect what? The top on this particular field to be valid. So guys, I will stop here. Excuse me. And if I continue to talk and talk and talk, there's still going to be more and more to talk about. So for now, in summary, force on a current carrying conductor produce only what? Magnetic field. Moving charge produce both magnetic field and what? Electric field. Static charge produce only electric field. Combination of the two, magnetic field and electric field, is called Lorentz force. Keep it in mind. By law, whenever you have it, the force per unit length does not depend on the what? On the current. It's only what? The force per unit length depends on the what? The magnetic field. So it doesn't change. It remains constant. Sensitivity of a galvanometer can be theta over I and can be I over theta depending on the what? SI unit. Keep that at the back of your mind. And for that, you always remember the torque, panning. The angle is always perpendicular and sin 90 is always 9 1. So these are ways in which we do this. Always keep in mind that you can convert AC to DC. You can convert DC to AC. For now, we have only limited ourselves with force on a current carrying conductor. We talk about dynamo, which is our generator in our house. We said they use commutator, which is also called split ring. The work of that is to allow current flow in one direction. When we get to electromagnetic induction tomorrow, by the grace of God, we are going to talk in an extensive way on all these conversion from dynamo to AC, from AC to DC, and other Faradays and links. See you guys soon. If you find anything interesting, consider subscribing to this channel and share the content with your friend. Bye for now.